Morning, everyone. Thanks a lot to the organizers. It's great to be here ahead of the French strike. I'm Matthieu Bloch, and I want to present some of the work that I've done with two of my PhD students, Shi-Yuan, who graduated recently, and Shang-Jen, who's about to finish. And the topic I use here, of course, I will go about the details of what I'm doing and why, but I think I chose this one because I think it exemplifies a lot of the challenges that I think would be of collective interest that have to do with how do you make a quantum link, whatever that link is really used for, work well in a way that's efficient. And, if you come from communication theory, resource efficiency is all what communication theory is about. But in quantum, what's challenging is we're not just talking about bandwidth or power. Usually you have all the bandwidths and no power because you're quantum, but you're worried about the quantum resources such as entanglement that are really crucial to show some advantage. And so this talk here today, I will try to exemplify, I think, what are some of the key challenges that prevent us from doing quantum the way we used to do classical. And the motivating thread for that is this work that we've done, inspired by some of the work that, of course, Bloch had started 10 years ago on covertness. And we're going to look at what we call robust and resource efficient covered here, quantum communication over bosonic channel. Okay, so I'll go through the proper motivation, but again, I think I want to distill, a few challenges that are really required to make quantum, either more accessible, more manageable from a communication theory and networking perspective. And feel free to interrupt me, yell at me, disagree with me. I think it's a nice venue for that. All right, so the big picture that's going to serve as a motivating thread for today is this model of communication over a quantum channel that's called a bosonic channel. So we have a transmitter named Alice trying to transmit a classical message. So we're going to focus on transmitting classical information over quantum channels. That classical message is going to be phase encoded, and I'll say why I'm already restricting myself to certain modulation, transmitted over a channel which is the equivalent, if you wish, of the Gaussian channel. It is a beam splitter. There's a transmissivity that reduces the amplitude of your signal, and there's an interference with some noise, which we describe as a thermal noise. So that's essentially a Gaussian channel viewed from a quantum perspective. The two outputs of your beam splitter are going to be received on one hand by a legitimate receiver we call Bob, whose objective is to recover the message that you encoded. And at the same time, there's an eavesdropper, and the goal of the eavesdropper is to figure out if you're doing something on the channel or not. So more specifically, the transmitter always has a choice. They can encode their message, but then they can decide, oh no, I'm actually not going to transmit. I'm just going to put vacuum. If you just put vacuum through that channel, because there is noise, you still observe some fluctuations at the output of the eavesdropper. And so the eavesdropper has to decide, am I observing some noise, which is represented by that state sigma 0 over n channel uses, or am I receiving a coded sequence? Now, if you code, you introduce dependencies all the time. So the state is potentially much more complicated when you code. There is structure in it. When there's noise, it's this product structure, and you're trying to decide as the eavesdropper whether there's transmission or not. And because we're quantum, we're going to do some more fancy things. We're going to use entanglement as a resource. And here, again, this is motivated by a system that I think can be very concretely implemented in the lab. We're going to restrict ourselves to a very specific entanglement source that's called the two-mode squeezed vacuum. And I'll remind you of the definition if you don't remember. That is essentially allowing us to encode the phase onto one arm here before we transmit, and the receiver effectively has the second arm as a reference. And we allow possibly the use of secret keys to coordinate. The key thing is that this quantum resource, it will offer capabilities that no classical resource can offer. And the question is, what can we say here? What is the fundamental limit of, say, the number of bits you can communicate to be reliable but not detectable? And crucially, how many such entangled resources do you need? The premise is that quantum resources are expensive, so we want to understand what is the bare minimum we need to actually achieve some performance. So the main result that I'll show is something that's a little bit technical, but it goes back to a nice result obtained by, I think, Bulat and Saikat and Chris. I don't think Saikat, were you on that paper? On the TMSV assisted one, quantum one, I don't remember, but Christos was there. So it's a nice result that says, if you want to transmit a classical message over n channel uses, if you don't have access to a quantum assistance in the form of this entanglement resource here, you can only push square root of n bits. Okay, it's pretty bad. You take a huge penalty, but that's because you want to be undetectable, and that forces a strong limit. But if you're able to leverage entanglement, suddenly you get a log n boost. And of course.
Is it always mixable entangled there in both entangled source?
So the assumption we're making here is that we have a TMSV. There's no noise. We're not, corrupting the entangled state. So that's a strong assumption that we're making. We have this perfect entanglement. I think it's still a little bit up in the air what we can do, but I think probably you can tolerate a bit of degradation, but I don't know if we ever quantified that.
That's NCW 20. Pass onto the to the either of these single orders. The goal of them is retained. It's okay. If you put noise, it goes away. And it has it considers a property, it teaches the property of that's a little bit of noise. All of them goes away, but the constant
remains.
So, still writing something in journal, really guide functionality. We don't get a congress. This is why it's so beauty.
And Christian, to your point, one key assumption I'm making is that somehow I have this magical network that allows me to use entanglement. How you would actually make that happen for real at long distance, that is a bit questionable, especially because this sort of entanglement we're looking at is like based on these optical modes. It's like a continuous variable really that you're transmitting that's very sensitive to noise. So realistically, I think what you would want to do if you were to ever build such a system, you would have to find a way to share entanglement that's robust. And then you have a conversion system that allows you to transduce from whatever modality you have into photonics. So in theory, these things are doable. How to do that for real, that remains an open question. But I'm assuming I have this entanglement distribution network. But my goal is to use it as little as possible. And I mean, Uzi is not here, but Uzi has this nice series of work where he looks at creating these coding schemes that are robust to, possibly the entanglement being absent. And he has sort of like these universal codes that work in both. Exactly. So this is like a nice way to think about how to be robust to loss in entanglement, but we're not considering that here. So Bulat had shown this square root n log n. What I'm going to show you is that you can actually get away with only square root of n TMSV pairs. And that's our main contribution. And I'll show you why. So why it matters. I'm claiming TMSV signals are expensive. These quantum resources are expensive. We can discuss that. I think in the end, it kind of depends on how much money you're throwing at your system. But we're trying to use them effectively. And previously, I think people had shown you had to use n such TMSV signals. So we're reducing the number quite drastically. And the way I think about these problems is I should not have to pay $2 to get $1. So if you think about covered communications, you're only getting square root of n bits, maybe square root n log n. You don't want to be spending n or, exponential n resources to get that. That seemed like a really bad deal. So that was our motivation. And perhaps one of the things I really want to highlight along the way is the set of tools that we've been using. Because these tools, in my opinion, they're very classical. There's actually not that much quantum. I mean, of course, the quantum shows up in the calculation, but the reasoning is very much in line with more traditional communication theory. And I want to make a case that there's probably a lot we still have to do to make the quantum world more accessible to people who are not trained in quantum and to show them that all their thinking, their training actually is very relevant. And there's a lot to be done. Sounds good? That's kind of like the three things I want to touch upon. Okay, so just to put everyone on the same page, there's been a lot of work for the last 2 decades and a half on understanding how much classical information you can transmit over such a quantum channel. Again, it's called a bosonic channel, characterized here by a transmissivity I call kappa. There's some noise. which is characterized by a mean photon number that you're injecting. And typically you have a mean photon number constraint at the input. And your goal is to answer the classical questions from Shannon: how many bits of information can I push through that channel and reliably decode? The twist is that you may have access to entanglement, which here is described very generally in terms of this bipartite state. I'm not even specifying here what that really is, but you can ask, what's the best I can do? And it's actually a little bit surprising how the study of these models came about. So just to be a little bit more formal again, so I have a quantum channel that has one input A. In quantum, it's very natural to always think about two outputs. You have your legitimate receiver's output, but then you have the environment. And if you want to think about the environment as an adversary, it's very natural in quantum. So quantum always has an adversary, whether it's a very harmful eavesdropper or not, that's for you to decide. But the environment is always there because whatever photon you don't get at the receiver is lost to the environment. You have a transmissivity kappa, mean photon number, and B for the noise. The thermal state, you can think of it as a Gaussian modulated coherent state. It's a state that is actually very nice because you can express it very nicely in the Fock basis. Every state is described in a Hilbert space. The Fock basis is a countable basis that counts the number of photons you can receive. And it has this nice property, it's diagonal in that basis. So it's actually a pretty nice state, and the statistics are very geometric, very easy to control. Often you'll see me talk about NT, which is a scaled version of NB by 1 minus kappa. Okay, so that's the model. The classical capacity of this channel is something that you could guess. If you do some quick calculations, you can convince yourself that, if you compute the mutual information, sort of play around with that, tinker, you can convince yourself that this should be the answer. Proving it is another story. It actually was only really formally established about 10 years ago, I think 2014 maybe. And it's a very clever proof because the achievability is not that sophisticated, but I think the converse is actually much more complicated. And ironically, the entanglement-assisted capacity is something that was established in the early 2000s by Bennett. So it's very easier to characterize the entanglement-assisted capacity than the non-entanglement-assisted capacity. So for those of you who might not be familiar, let me try to decipher. The reason that function g comes in here, g, is this x plus 1 log x plus 1 minus x log x. The intuition is that it comes from computing a von Neumann entropy. Entropy has this x log x, so that shows up quite naturally. What's a little bit more sophisticated is that you have to use symplectic decomposition to get through the math, but despite the seemingly ugly nature of that expression, that follows quite naturally by direct calculations once you understand what you have to compute. But the one thing I want to point out is that I think the reason why this entanglement-assisted capacity came first is you can think at the first order very naively as entanglement is like common randomness. And so if you have a lot of common randomness in your system, if you want to write a proper coding theorem, it's actually a little bit easier because you can treat everything like it's an uncoded system. What makes coding theory and some of the information theory related to that complicated is that your system is not coded, is not uncoded. You're encoding a message into a sequence of length n, and there's a lot of time dependency, and that requires sophisticated tools. In a way, if you do everything with a lot of common randomness, everything looks like it's uncoded. So I think that's why I think it came about a bit more easily. And again, the converse for the classical capacity without entanglement assistance is a very sophisticated. So that's kind of the lay of the land. And the main message is that there's a benefit to using entanglement. You can look at the ratio of the entanglement-assisted capacity to the non-entanglement-assisted capacity, and it scales like minus log over ns. So think about ns as being very small. You have very few photons in your signal. And so this could actually be a quite large quantity. So what it's telling you is it's telling you the fewer photons you have, the bigger your quantum advantage. So it's good news for quantum. It means quantum is really useful for something. It's bad news for people who want gigabit throughputs because the quantum advantage is more pronounced when you actually are severely limited in terms of photon numbers. So you're never going to get gigabits per second. So, just thinking about distilling, I think some of the key challenges we have when we talk about these entanglement-assisted networks or quantum networks in general is we have to make a case for why it makes sense to use resources that we know are going to be very scarce, very fragile, and provide some advantage at scale. Because we know the quantum advantage shows up when you don't have many photons. And it's possible to come up with such examples, think about quantum key distribution, sensing improvements. I mean, there are cases you can make, but it's never going to be, you're going to get 10 gigabits per second throughput that is quantum protected. I don't think we're there yet. Saikat?
One, you're absolutely right. It's the low brightness regimes where so by most first eyes, and also the advantage now to any margin that also the bigger challenge that you're operating effectively in a long wave there and squeezing like supported microwave domain.
That's a good point. No, you're right. And, especially, like the systems we have in mind here are optical photonic systems. It's very easy to have huge bandwidth, right? So when you think about the per mode, as like I said, you multiply by the actual number of modes, assuming you can address them independently, which sometimes is not quite as easily done as said, but you can potentially still get throughput. Anecdotally, I remember I got a call one from a company who was very good at designing these amazing receivers from satellite to Earth, satellite to ground. And they were like, oh, we want to do some quantum key distribution to support. We have this nice gigabits per second link. And I just ask, what's your loss? Oh, no, 30 dB through the atmosphere. You're not going to get much quantum benefit through a link like that. But you're right. I think you can scale up by number of modes. So that's the lay of the land. It kind of shows you. But what to me, motivating factor is that the regime in which NS is very small, it's a regime where talking about undetectable communication becomes actually quite natural. So that was a nice motivation. These things are real. This is as real as it gets, I guess. This is a photo courtesy of our colleague Shang-Jen at the University of Michigan. I believe that's the experiment he used to do not covered communication, but covered sensing. So it looks a little bit messy. We're not quite talking about an off-the-shelf product, but all the phenomena that we're going to rely on, they are real and they can be measured and really used in a lab. The last thing I wanted to mention is that people talk a lot about demonstrating quantum supremacy with computing. And of course, it's very flashy if you can say you can break RSA, makes people very scared. But the reality is we've already demonstrated quantum supremacy in communication and sensing. I don't think it's making us splashy news items in the popular literature, but it is actually something that's much more concrete today. And this is a very nice experiment by, again, Shang-Jen and his collaborators, where they were trying to demonstrate that indeed that quantum boost that you're getting with entanglement is real. So this is the system they used. They had a classical message, phase modulated, transmitted over a bosonic channel with assistance of a two-mode squeeze vacuum. So two-mode squeeze vacuum is, again, one of these nice states that you can represent the Fock basis quite easily. It has some interesting statistics. And they have a real receiver. I'm not going to talk about it, but they know how to exploit this entanglement with a concrete optical system. The figure I want you to draw your attention on is the one on the lower right. So the red region here is the classical regime. And we know from Shannon, there is a converse. We can only transmit so many bits per second per hertz, if you wish, or here bits per mode. This is parameterized as a function of the thermal noise, mean photon number, and then looking at the information rate in bits per mode. As you can see, the blue region is what you can theoretically achieve with entanglement assistance, and experimentally, they've been able to sort of achieve at least some rates that beat the best classical converse. So this is a demonstration of quantum supremacy. Of course, it's not as splashy as saying you broke RSA, but this is real. So you can definitely, we know experimentally how to leverage entanglement assistance to beat any classical system. And so the theory matches the experiments. As you can see, we're barely in the quantum zone in this experiment, but the first step is the hardest one. These things can be scaled up. So all that to say that entanglement assistance is real. It's not just on paper. You can actually build system. All right. So maybe this is my main provocative slide for today to spark discussions. So if you think about communication theory, there's actually a big difference between quantum and classical. And I tried to highlight that along a few dimensions, which I think are more telling. The first one is data rates. I mean, quantum right now is low data rate, whereas classical, we want to go as fast as possible. And Psycat's comment is on point. I mean, there's something a bit more nuanced about this. We have to be careful. But if you're willing to go, the high number of mode argument, it also works classically. So per mode, quantum, much lower data rate than classical. The resources that you need to enable communication, unfortunately, in quantum, they're expensive. I mean, you can just look at the dollar amount that you need to build a quantum system. Of course, the classical world has benefited from the dot-com bubble, where suddenly we flooded the world with technology that reduced the cost. But we're definitely not there yet in quantum. The systems are also not very robust. Quantum states are very fragile, as Christian was alluding to. If you have noise, you start destroying things. If you have losses, maybe you can tolerate them, but you have to really look at it carefully. Whereas our classical system, they're pretty robust. I mean, we're all on Wi-Fi and cellular right now, and it works. We don't think about it. Receiver design is another one. The receiver designs in quantum is still very complex. I don't think this dust has settled onto what is a way to design a good receiver that would be, powerful enough to be modulated to whatever system you want to look at. Whereas in classical, this is very mature. I mean, you learn in digital communication 101 about the, matched receiver. You design a match filter. You know that whatever modulation you can adapt, and then you forget about the receiver design. Like you leave it to the people who build systems to design it. And we work directly in this, sample discretized world where everything works fine. In quantum, that's not there yet. There is a theoretically optimal receiver that people use all the time, but it has no concrete implementation associated to that. At the system level design, in quantum, there are few simple models. Arguably, if you look at the success of communication theory for MIMO and whatnot, it's because ultimately everything is a Gaussian channel. Maybe you put a little bit of fading and then you can deploy your tricks, but there's this consensus that these models, no matter how simple they look initially, they're very robust, meaning they actually are representative of the real world, and they're very useful abstractions. If you design a system based on that in simulation, the experimental verification you have to do downstream will actually match that. Like if you show a gain using some sophisticated, MIMO system, there's a good chance it's going to work out nicely when you actually deploy the system. I don't think that's true in quantum. And finally, the last challenge, which is, I guess, a bit closer to my heart, is if you think about information theoretic limits of information processing, the good thing is this mutual information that Shannon, presented as the fundamental limit of communication and has an operational meaning, it's very solid. It's also nice, like I of x, y, it has these nice analytical properties. You can then take it, squeeze it, change what x is, put constraints, and we can still numerically and analytically go very far to get intuition. When you look at the corresponding information that matters, transmit again, classical information over quantum channel, that's the whole level information. That is a different story. I mean, you can compute it numerically. There's been a lot of progress. There are packages you can use to get some intuition, but it's nowhere near as simple as the classical information. And I think that's a problem, in my opinion, because if you think about communication theory journals, they're usually taking all of that for granted. And it's not innocent because it means you can talk about, I'm going to optimize I of XY over a channel. You're completely abstracting the fact that you need a real code. You're essentially saying the uncoded version of the system is all I need to study, because then the engineers can throw in an optimal LDPC or polar code, whatever you prefer, will kind of the folks who build the circuits will build the match filter and everything will work. We're nowhere close to that in quantum. And I think that's why there's no real quantum communications engineering done at the scale of classical communication engineering. We're missing, the key tools that allow us to be convinced that indeed all these assumptions we take for granted classically will again hold. But I think it's an opportunity because there's a lot of work we could do to actually help with this. Maybe there's a way to think about the way we, which quantum states we use or what system we need to build to make them more robust. Maybe there is analytical work we can do that allows us to analyze these information theoretic quantities in a way that still provides the high-level system level insight that the network engineers like, because they abstract the links. So I think there are plenty of opportunities there that we can exploit. And a lot of what we did in the specific work I'll briefly mention is actually motivated by that, like trying to get a bit closer to classical communication and networking. Does that make sense? So there's a lot of really fun stuff to do. Now, if you're somebody who says, well, I don't care about analytical things, all I want is a simulation and have a data-driven solution, none of what I'm going to say is really going to matter, just to be clear. But when you start talking about networks, I don't think the network people think like that. I mean, they like to be able to say, I'm going to create a network of nodes and I'm abstracting the actual links. So this abstraction is actually crucial. They don't go down to simulate the actual propagation of waves. No one does that. So you need to provide these intermediate layers of abstraction. And I think for quantum, there's still work to be done. So 2 takeaways from today's talk, and I'm talking too much again. So takeaway number 1 is that actually you can take this communications engineering state of mind and apply it to quantum. There's a lot we can do. Takeaway number 2, there's a lot of classical tricks that you can play to improve quantum systems. Because if you believe what I said earlier, that we want to be careful with how we use entanglement, it's a resource, and we know a lot about how to be efficient in resource allocation problems. So that's my 2 big takeaways from the talk today. All right, so let me go into the slightly more nitty-gritty details of what we did. So we're back at this model where we're trying to say there's a no communication mode in which you send a vacuum state, in which case the receiver gets a state I'm going to call rho 0 in product form over n channel uses. But I could also try to communicate, in which case there's a public code C that represents what happens when I take a message, k bits, I encode them into n modes, transmit them through the channel, and I choose my message uniformly at random. So again, I want to highlight that this state I call sigma hat wn, it's a complicated state because you're choosing your message at random. So your state is actually an average of states. It's a mixed state. These are notoriously hard to analyze. It has a lot of structure. It's not that clear. It's not ID for sure. Bob attempts to reliably recover W hat from your coded sequence, and the goal is to escape the detection of the adversary. I'm going to call it Willy the warden. And the eavesdropper has a pretty simple goal. It's running a binary hypothesis test, hypothesis H0. There's no communication, and I know the statistics or the state I'm supposed to get. Hypothesis H1, I observe that mixed state resulting from the encoding of information. And Willy is allowed to do the best detection it can. So we want to make sure that when we communicate, we're not only reliable, but essentially we're preventing detection by forcing Willy's optimal test to be no better than a blind test, which would be operating without looking at the channel. Okay, so when it comes to being undetectable, you're not preventing Willy from making a decision. If they want to say you communicated, they can always claim it, but they cannot build a statistical test that would be better than just a random flip of a coin. So it's not statistically significant. All right, so if you want to be, oops, what happened? Some equations are missing. All right. So I'll skip the details. So the key thing that we looked at is, what do we know? So in the classical regime, there's a very nice set of results by Bulat, Saika, Don Towsley, and Denis Gackel from over 10 years ago that showed if you want to be undetectable, you have to operate in a regime where you can transmit very few bits. And that's sort of intuitive if you think about steganography. If you want to embed a secret message in an image, you cannot distort the image too much. So you can flip a few bits here and there, but the number of bits is severely limited, and it has to be on the order of square root of n. In the quantum regime, there are some really cool things that happen. Again, you can sort of beat the square root limit, which is classical, by using entanglement. That was shown in a series of papers, and then you can boost the scaling by log n. And log n doesn't seem like much. I mean, log of 10 to the 10 is still 10, but because square root of n is also not very good, this is actually not a trivial improvement. The initial results were a bit vague in terms of how many entanglement resources you need. And if you deconstruct the proof is based on a completely inefficient use of entanglement resources. There was a follow-up set of results in which I don't think, correct me, Bulat, it was not super explicit, but the result shows you can reduced to n modes. Like when you went to a more practical implementation of these receivers, think about how the encoding is actually done. I think you can show that you can get away with n TMSV pairs, even though it's not stated as such. But that was already a huge improvement. But n versus square root n log n is still very expensive. You need to put n entanglement resources to get the throughput of square root n log n. And our contribution was really to show that you can make something quite a bit more complicated, but that will essentially reduce the number of TMSV pairs to something that scales like square root n, but maybe you have to use a few secret classical bits to make that happen. Okay, so my goal today is to show you how we got there. And since I lost the slide with all the fine technical details, I'll keep it high level. All right, so the proof approach, I think, is something that that I want to highlight. Let me skip that. Let me talk about our approach. So we actually took a few very concrete steps that are not trivial. I mean, they're not complicated, but they have to be there for very specific reasons. So the first thing is we use the phase modulation. So there's nothing that tells you have to use phase modulation. And if you remember digital communication, phase modulation is nice, but if you can do QAM, you would do it. Like it leads to better performance. There is a regime where phase modulation, like just phase shift keying, is good enough. But in general, more advanced modulations perform better. But there's something you should also remember: the coding theorems, from classical information theory, they don't really use this discrete modulation. They're based on Gaussian modulated, abstract signals. And this Gaussian modulation is actually not something that you would necessarily do in practice. You can try to mimic it, but we always start with finite constellations because that's what we can do in hardware very well. In quantum, there's something a bit funny, which is that your coding theorems, that allow you to write I of xy, putting whatever distribution x at the input, they don't quite hold as generally. And actually, the coding theorems, especially for the sort of bosonic channel that happen in infinite dimension, they work when you have a discrete modulation. It's not clear to me that they work so cleanly in their more general form if you have you say you have a Gaussian continuous PDF to do your modulation. And so if you want to be very precise, it actually helps to start with a finite size modulation. So starting from PSK was important for us.
Yeah, touching against
of course.
Your entanglement generation is also covered, but it might be problematic also.
So we're not looking at the cost of entanglement generation. So we're looking at this following. We're assuming that we have an on-demand system. I can query the network and it will deliver a perfect TMSV. This is absolutely the next step, right? We need to think what happens when the entanglement generation is maybe not on demand, but maybe imperfect. I'm assuming I have quantum memories. Maybe I don't. Most likely I don't. So, there's still a lot to bridge. But that was the simplest model we thought that, captured the essence of the problem without getting into these details.
So, one quick question. This state or proposed results.
Oh, that's a great question. So this formalism here of covered communication, it is, I think, fairly tied to how you define the problem. So let me tell you exactly what I mean. It doesn't matter so much what you call zero. I mean, we choose the vacuum state. You could try to do something, but one thing, you could try to do something else. But one thing that's very important is that my reference covered communication problem requires me to put a deterministic input to my channel. So if you were to change that and you were instead allowing something that is not a fixed state, let's say a mixture of different states, then your results could change quite drastically. The square root n scaling that Bulat identified is very much tied to you asking your coded system, which creates a mixture, to mimic the behavior that you obtain when you have a deterministic input to your system. If you're allowing your reference system to be stochastic input, then the results change quite drastically. Now, intuitively, I think it makes sense to say you have a reference system where when you say no communication, it means do nothing. It makes sense to put vacuum, but you could say, well, maybe my reference system is I have some background communication. And that's what I'm trying to mimic. But then it's a different regime. I think it's called stealth. I think Gerhard Kramer and his students called it stealth. And there is no square root n. I mean, everything is the classical information theoretic regime. A lot of the tools do map quite naturally, but you don't have this kind of magic boost in entanglement in that regime.
You could help investigate that there might be, in country it's called a relative sequence view. So people say, those were described in the non-deterministic. That hasn't started to look at the quantum past quantums. Yeah. Regarding Krishna's question, please choose entanglement. Where he can consider that who can with entanglement, me, myself, and open up to it. How else to distribute bits? We don't want to distribute even see it.
No, exactly. So I'm very much tied here to a photonic experimental system. So let me try to highlight the tricks that we use. So this one is not completely from us. We made it maybe a bit more formal, but that addresses one of my earlier points about the difficulty of getting theoretical mileage, theoretical insights with some of this complicated information, theoretic quantum quantities. So I want to talk about why it's so nice to talk about phase modulation. Why don't I talk about a more general modulation from the get-go? So the challenge we have is the following. So imagine, you have a TMSV and you're applying a phase modulation to one arm. You're going to choose your phase modulated states uniformly at random. So you're effectively creating a pretty complicated state. It's a mixed state because you're creating a mixture based on the different phase modulations that you apply. And mixed states, they're notoriously hard to analyze. Even though a TMSV is a Gaussian state, the moment you apply the phase modulation, it becomes non-Gaussian. So a lot of the tricks, if you wish, don't apply quite naturally. And so what that means is that if you look at the density matrix and you express that in the Fock basis, in principle, it's a very complicated expression with a lot of terms that depend on these four indices that correspond to the different number of photons you will find in the two modes of the TMSV. But if you plot it, so there's a nice package called Walrus that allows you to decompose states in the Fock basis. You can actually plot. So just to be clear, I have four variables here, and I'm trying to collapse that to a 2D plot. So let me tell you how we did this. What we did is we sort of put a cutoff on the max number. We don't go to infinity, we go to 25, and then we parameterize on the x-axis by n1 plus capital nn2, and on the y-axis n bar 1 plus capital n bar 2. So we create a cutoff, and then we index the different components a bit differently. But then you clearly see there is a lot of structure. So the phase modulation actually creates a lot of symmetry in your encoding that translates into a nice structure in the density matrix. And when you increase the number of phase modulated states, some magic happens. You see some of the diagonal terms disappear. And so what it suggests is that as you increase the number of phase modulated states, this seemingly ugly state, which is non-Gaussian, definitely not diagonal, actually converges in the limit to a non-Gaussian but diagonal state. So a diagonal state, think about it this way. It's effectively something you can handle classically. And so we can characterize actually quite easily is not the right word, but through calculation, you can characterize the limiting state. So this is a non-Gaussian but diagonal state in this Fock basis. And the coefficients you can express explicitly in terms of a hypergeometric function. So I think the first time I saw that is a paper by Xuntao Zhang. Now, what we proved is we said, okay, that's nice, because if you know you have a diagonal state, there's more likelihood that you can actually do and compute something with it. But it's important to know how fast you get to that diagonal state. And so we did some work to show that under some conditions, you can ignore the details, but it means you need to be in a regime where you have enough thermal noise for that to hold. we used some really cool result from Sycat and his former student, Michael Grace, who's now at Raytheon, to actually show that the convergence in terms of fidelity between an L state modulated PSK, 2 to the L modulated PSK state, and the limit is extremely fast. So your convergence is actually exponential in the number of phase modulated states. So that's good news because it means that you go to 16 PSK, you're probably very, very close. Not very probably, we actually know exactly how probably we are, but you're very close to this limit state. And so instead of trying to compute exactly the performance of an LPSK module or to the L modulated state, you can go to the limit directly and sort of account for the penalty. And so that makes things a lot more tractable. So that's probably the main trick that we developed is we have a really good understanding of how suboptimal is, what's the gap between very sparse PSK modulation and a very dense one. Because this is a hypergeometric function, it's not that easy to manipulate because behind a hypergeometric function, there is a series. So if I were to ask you, okay, this is the form of your state, do you have any intuition regarding the whole level information that is generated by that state? It's hard to get because it's closed form, but the dependence on the parameters is quite complicated. So let me skip this one. So I just want to mention, again, briefly what I mentioned earlier. If you accept the fact that it's easier to manipulate states which are diagonal in the Fock basis, what we did allows us to say, let's focus not on a fixed 2 to the L modulated PSK constellation. Let's look at the limit of very, very dense phase modulated constellation where you have a uniform phase modulation. Effectively, that's easier to handle, but then we can capture the penalty that we pay. So we can compute the whole level information for a continuously uniform modulated phase and then subtract the penalty, which ends up being very small because the convergence to the limit is extremely fast. So that's trick number one. I could be very precise about that. And then because of that, what we've done is we've been able to analyze analytically what is the whole level information where you're using this continuous phase modulated state. And to show you why it's useful, I'm plotting here the performance of an entanglement-assisted communication system in terms of the ratio between the entanglement-assisted capacity and the non-entangled one in the NT, which is the thermal mean photon number in your thermal noise, mean photon number in your signal plane. What I'm showing you here are the level sets of the ratio. Okay, so if you see a 1.5, it means the entanglement assistant gives you a 1.5 multiplicative boost compared to the classical non-entangled capacity for classical information over quantum channels. And you see 12, you get almost more than a factor of 10. So this is the result that we know from Bennett in the early 2000s. As you can see, it's telling you the more gain, the best gains appear when you operate with very low mean photon number in your signal and very high mean photon number in your noise. And what we were able to do is we have a closed form expression for the rate, for the ratio, if you wish, when you're using phase modulation. So this red curve is actually analytical. It's not a simulation, it's analytical. Our bound doesn't always hold. So there's a regime where you don't have enough background noise where our bounds don't hold. And we were able to get, so as you can see, the level sets are not always matching the optimal ones. They're actually a bit tighter, which is an indication that if you restrict yourself to phase modulation, you are losing something. For instance, you can only get the performance when there is enough photon in your noise and you don't use too many photons in your signals. So in the top left corner, you see that the level sets are very tight, which means that phase modulation is almost optimal. But of course, as you go further away from that regime, our bounds get looser, which also indicates that phase modulation becomes suboptimal. If you were to do a pure numerical approach, you would see that phase modulation performs better than what we predict, but our bounds are analytical. So what do the bounds look like? So every talk should have a joke, so that's sort of my joke. So the approach is actually not that complicated. All you have to do is you have to compute a whole level information, which, like the Shannon information, can be expressed as a difference of entropies, your von Neumann entropies. You need to compute the von Neumann entropy of the mixed state, where you are looking at your uniformly modulated state here. versus the average of the conditional ones. The second part here is easy. That's already been done. The trick is to compute the entropy of this mixed state. Because if you remember, we showed that it's diagonal. The good news is that this von Neumann entropy is actually a classical entropy. Okay, so far so good. And so we actually know the classical distribution. That's the one that you obtain by looking at the description of this quantum state, which is diagonal in the fog basis. So all you have to do is compute. Now, the challenge is that this is not particularly nice. And the goal is to figure out if you plug that in, that expression, what does it tell you about the behavior of the system? And again, this hypergeometric function is an infinite series. So all you need is some calculations, Mathematica, MATLAB, lots of coffee, dedicated grad students. We actually did not use ChatGPT at all for this. We didn't know. So we didn't even try. But after that, you get a nice expression like this. Okay, so that's my joke. It's not particularly nice because it's the result of many things. Essentially, the only way we could get a bound by very carefully truncating these infinite sums. And it's the first time in my life where we really had to use, so much coffee for sure, but also MATLAB and Mathematica to make sure we were doing something that made sense. Because we could not use Mathematica directly. If you say simplify, it does nothing useful. We had to figure out what to truncate. And for that, we had numerical simulation. And then we had to check back our calculation with Mathematica. So it's ugly. I mean, let's not kid ourselves. It's ugly because of the truncations we do. But then what it does, if you look at the first terms are actually likely the correct ones in the expansion. They show you that the interplay between the physical parameters that determine your system is very complicated because the noise matters, the transmissivity of your channel matters, and the number of photons you put in your signal actually matter. And the interplay is actually not that evident. People understand the first order terms very well. There's no news thing, but I think we're showing that the second order is actually much more sophisticated. And you could say, okay, this is all great, Matthieu. I mean, that's a lot of work for an expression that's not very insightful. I'll add one thing. A lot of the calculation physicists do, they jump around a couple of issues. One is you don't really characterize the quantum regime. You just say, I'm going to operate in a regime when I have few mean photon number in my signal, high mean photon number in my noise, and often a low transmissivity. But you don't quite define what these are. When does that regime kick in? One of the benefits of that approach is that the bounds I'm showing here, they're actually non-asymptotic in the physical parameters. So if you're a system level engineer, you can sort of start to use these bounds to think about what is the power I need to put in my system? What are the resources I need to throw to hope to see some quantum effect? So it sounds like nothing, and in the grand scheme of things, it is not a whole lot. But I don't think there are many works out there that are really that precise to tell you how the physical parameters, which you might or might not control, will result into some quantum advantage or not. And Saikat, you had a question.
I was wondering how general is this in terms of applicability to, say, the non-entanglement assisted case? So if I take, say, a coherent state or a lossy thermal noise channel, and I want to know the convergence rate as I increase the PSK order for the just Polevo capacity.
No, excellent question. I mean, so that's legit. I mean, this is nice, but is that like a measure zero result? So the answer is that it's not measure zero. So I don't remember if we've done this one specifically, but we've played around with that a little bit. So one thing we've done, I can mention, because it's on archive already, I think, is that instead of modulating TMSV here, if you were modulating, say, a displaced thermal state, so I don't remember if we've done the coherent state, but displaced thermal state, you end up with something quite similar. What changes is that in that expression, that density changes. Like we end up, for instance, with a different hypergeometric function. So we have to deploy the same machinery again, but at least we've been able to extend it beyond that. So the case you mentioned, I need to check if we've done it, because if we have not, we should, because that's a very natural one. But the framework does seem to work. And again, the steps are always going to be the same. Try to check if the phase modulation symmetrizes your system enough so that your non-Gaussian state becomes diagonal. And that's going to be true because of the nature of the phase modulation. To characterize the density matrix in the Fock basis. which inevitably will have these hypergeometric functions because that's a reflection of where your photon goes when they start impinging on a beam splitter. And then use the tricks that we have used that tell us when to truncate these sums to reduce the calculation to computing moments of order no more than 2. That's really what we've done. And that framework is quite general. So when I talk about the truncations, the challenge is that this is completely ugly. But if you truncate properly, you can show that all these calculations reduce to compute certain well-controlled moments related to, geometric distributions. It takes some effort to actually get there, but once you understand what you're after, it's actually more general than it seems.
May have thought about this, Matthieu, already. Something that just occurred to me. Are you familiar with this few papers done on quantum reading? This was back in 2010, 2011. Jeff Shapiro and I had a paper, and then Stefano Piranesi.
Oh, yes. I remember Stefano's paper.
So it's very related problem to entanglement-assisted communications. And I think your results apply there.
Okay.
The setting is that you have a memory that you're reading passively. Okay, so unlike communications, you're not allowed to do active modulation. You cannot send a coherent state. So your memory just puts a phase modulation or reflectivity modulation, and you can send states and you can retain entanglement. And there also, so the turns out that the capacity is restricted. It's not the G function capacity because you cannot do active modulation. But if you use entanglement, then you can go back to that G function capacity with only phase modulation. And the approaching that level capacity with the order of the PSK would be very interesting to look at there.
Okay, nice.
So
something
that
to
would apply.
Talk about over lunch. That's awesome. Yeah, I hadn't thought about that. Thanks. So, in the grand scheme of things, it took a lot of tears from me and my grad students. I kept track of the coffee bill because the deal I made was whatever coffee you need, I would pay for it. I think I exceeded $600 that month. But so the long story short is that these are things that are very natural to do in classical communication theory. Right? You play with I of x, y, and then you say, what if x is restricted to that constellation? And you get all these engineering insights. Doing that in quantum is much more complicated, but I think in some cases, it is doable, and it kind of pushes a little bit beyond what the physicists already know. I think they know the behavior of this function, but they're often like a zero or first order. If you want to get something that's not asymptotic in the physical parameters, you need to do that work. And so we sort of have a recipe to do that. So the second trick I want to mention is, let me go back to this entanglement resource, and I'll finish with this. The second trick we use here to be efficient in terms of the use of quantum resources is to use coding. So let me tell you in as clear of a way as possible what's going on. If you want to be undetected, the intuition you should have is that I should use very little power, right? If I have very little power in my system, I'm going to be harder to detect. And then the second thing you have to think about is you also need to hide the structure of your modulation. Because if you just use a little bit of power, but everyone knows you use power at the beginning of your transmission, people can ignore the rest of your transmission. So you need to do two things: low power plus hide the structure of your transmission. Focusing on the low power first, there are two ways you could think about having low power. You can either use what we call a diffuse modulating scheme, which means you're using a very, very low power at all times. So think about taking your usual signal, you just crank down the amplitude a lot, you're going to have very, very low power at all times. But you could also think of it as, I call that diffuse signaling. So you take your constellation and you shrink close to zero, if you wish. The second approach you could say is you're going to play with the duty cycle. Instead of saying I'm going to transmit very little power at all times, you can say maybe I can transmit a bit more power, but I'm going to do that very rarely. And you can convince yourself both approaches can lead to a small average power. If you use a sparse signaling, you could just transmit a lot of power, but very rarely that's the same average power. And so intuitively, you could say, well, won't the eavesdropper figure out I'm transmitting? Well, if the rate of occurrence of your transmission is compatible with the statistics it accepts, it's okay to have rare events even every once in a while. Just because you see, like if you think about Gaussian noise, it doesn't say that you can't have high amplitude, it just say it's rare. So as long as you don't violate that, you can also be undetected. And so both approaches are valid to get low covered communication. And what we did was combine the two. So the idea, I'm going to just explain this. This is a result that you can formulate that says if you control the power and if you control the sparsity, you can ensure that you're undetectable. We can make that formal. What I want to highlight is the operational trick we used. So the goal is to be covered, undetected. We know there's a boost from the quantum resources, but we don't want to use too many quantum resources. The trick we used was to say, let's actually think of our message as two messages, W1, W2. The first message, we're going to use a bit of a secret key. You can ignore the fine details of why. But that first layer of coding, we're just going to use it to indicate position. So you can think of me using on-off keying. I'm going to place a few ones here using some coded structure. So I'm still encoding information in the form of on-off coded sequences. But then these ones here, they're really just going to be a means to indicate when I should use the quantum resource. So in these positions, you're going to actually use a phase modulated two-mode squeeze vacuum. We're going to choose a number of ones to scale like square root of n. So we're actually only using square root of n quantum resources, and we're going to map them together. So whenever you have a 1 in the first layer, that is when you actually effectively use your quantum encoded resource. And so we're using sparse encoding. So there's a lot of sparsity in the first layer and low power in the second layer. So we're using these two tricks jointly, but it's through a coded system. So you can think of that as superposition coding. If you're familiar with the tricks on broadcast channels, that's exactly the same nature of the trick. And that is extremely powerful because effectively what it tells you is it tells you that the boost from the use of quantum resources really happens because the scaling of the capacity with the parameters of a TMSV has this very specific form, but the scaling actually only depends on the number of TMSV pairs that you use. And you just have to be very careful to hide the times in which you use the TMSV resources to still maintain coveredness. So we have this two-layer coding scheme, and that's a very classical trick. So again, very classical reasoning. This is something that comes from pure classical information theory, but that was enough to actually lead to a very efficient use of quantum resources. We don't know yet whether that's the best thing to do, in the sense there could in principle be a scheme that uses even fewer quantum resources than this, but we've made some progress on the converse, and we think this is actually optimal. You can beat that. So I'll skip some details. You have to argue that you can also recover that information because everything is multiplex. So how do you recover W1 and W2 separately at the receiver so that the receiver knows where to look for the quantum resources? From a theoretical perspective, all of that works. Doing that in practice, that's a big open question. That's becoming much less realistic right now. So I'll skip some. So we can characterize, if you wish, all the information rates as a function of the physical parameters. So let me just leave you on this high-level idea. So this model to us was very interesting because it really forced us to not only look at covered communication, which was interesting in itself, but think about all the tricks that we were used to manipulating in the classical world that failed. And so to obtain the results, we really had to deploy these three tricks. One, restrict ourselves to simple modulation schemes because they're much more analytically tractable, but then we could get bounds that were not asymptotic in the physical parameters. Two, sort of think about different mechanisms by which we could exploit, or achieve low power, either through sparsity and diffusion. And these different intuitions actually translate operationally in different coding schemes, which are very classical, but then you can operationalize that. And this two-layer superposition coding leads to an effective use of the quantum resources. So I'll leave it at that. And I just want to give a few pointers to show that this way of thinking, it's much more general than my little talk here makes it appear. I'm going to mention two papers that I just read recently. So they're not saying they're the best. They're very good, but I just happened to read them recently. There's a very nice paper by Eric Chitambar from UIUC. It's a PRL from just maybe a month or two ago, in which he looks at, characterizing like in a astronomy context, light that's coming from a far star is picked up by distant telescopes, and you want to distribute entanglements between telescopes to boost the detection. Now, you don't know a priori where the photons are coming, and so you need to optimize that. And it has very similar flavor. He's trying to optimize entanglement distribution. And the way he does that is he uses some sort of preprocessing on the light to make it more clear where the entanglement is needed. And even though it's not phrased at all the way I describe it in terms of superposition coding, there is a connection. You're doing these very weak preprocessing that don't disturb the states too much. That's our first layer in our case, that then allow you to concentrate the quantum resources where they are needed. And there's also some nice paper by Saikat and his former student in which they look at a problem of making a quantum entanglement assisted measurement in a distributed sensing problem, in which they look at more precisely what are the sort of measurements that you need to do to distribute entanglement effectively. And again, you have a lot of trade-offs that show up that suggest that you have to be careful if you want to use entanglement effectively, because it is related, of course, to the problem, but it's also very sensitive to how the quality of your resources and when and where you get the best bang for your buck. And staying in the spirit of the theme of the workshop, I think if we want to build this entanglement-assisted network, we have to think very carefully about when and where the resources are truly needed. And Christian already alluded to, are they actually robust to all the imperfections? So there's still a lot of work to do there. And to me, what's really exciting, and I'll finish with this, is that the reasoning is actually not quantum. It's actually, you can make very engineering-focused classical reasonings about resource allocations, and these intuitions actually will translate to gains in the quantum world. So I'll stop here. Thanks a lot, everyone.
Hi, Matthieu. Thank you for the great talk. I have a question about the main result. You have this square root of n log n, and you use about square root of n two mod squeezed states. You have, do you have lower bound for this square root of n two mod squeezed states?
Okay, so excellent question. So if you think about what we're trying to characterize here, there are two things we should worry about. One is, what is the maximum number of bits I can transmit classically that are reliable and covered? And that's one bound that you want to establish. So that's the first scaling of the number of bits that you transmit. And the second is, how many entangled bits do you need to do that? That's the second thing you want to characterize. So the bound on the square root n log n, this one is tight. So that's what Bulat showed in his paper. So if you don't worry about how much entanglement you need, you cannot beat square root n log n.
I asked the second.
But the second one is where we were trying to make progress, understand what's the minimum number of entanglement that you need to actually achieve that. So the square root n log n, that's optimal. The number of TMSV modes that we need, we are at square root n, which correspond to square root n log n e bits as well. We don't know yet if that one is optimal. Was I clear?
Yeah, exactly.
Okay, so it's like like in a classical way, you know your capacity, but you don't know how much randomness you need to achieve it.
Okay, so somebody can hope that they can get probably log n the same.
So what we think is, that the number of e-bits that you need is square root n log n. So our achievability shows that's the case, because your square root of n TMSV pairs that translate into square root n log n e-bits, but we don't know yet if that's optimal. We think it is. And that would make sense in a way, right? Because like nothing comes for free. And it would be nice to say that the scaling you get, square root n log n with entanglement assistance, actually happens because you are consuming square root n log n e-bits. That's our intuition, but we don't have a proof of that.
Thank you.
Just to follow up on that and answer Christian's question. So, right, and yes, there is no free lunch, unfortunately. We can, using a very, very complicated translation of the coding scheme that comes from DevTech, that takes a secrecy code and translates it into entanglement distribution code, we can transmit square root of n e-bits using square root of n secret bits in this channel. E-bits though, not TMSV. And for that, to create TMSV bits and TMSV modes at the rate that Matthieu can use, we're going to need square root of n log of n qubits. So that's kind of a kind of addresses yours and Christian's questions in a way. So it's right. But the Delta's approach, I believe, is considered optimal. There is an upper bound to actually have on the entanglement generation capacity because it's the secrecy bound. And Uzi, who has basically started all this in the finite dimensional case, me and him have a paper we're submitting to transactions this week, I think. And the other paper is under review, but it's also an archive. We have improved, the other, we can talk about it, but yeah.
Many thanks for your fantastic talk. I have a question, but I'm confused somehow. My question is a combination of Christian's question and what Bulat say. We know from classical information theory that Alsvide is considered the problem of common randomness generation over a classical noisy channel in the presence of a noiseless classical channel, and this context is extended to quantum work by Andreas Winter and Igor Devetic that is mentioned here. But my question here is that how we can generate quantum entanglement between Alice and Bob covertly. So I think we need at least a level of power to generate entanglement between Alice and Bob, but how we can do it in your system model covertly. So it is not clear to me. Yes, exactly in this slide.
So, I mean, I agree. And so we have to be careful with what we mean by coveredness. So my definition of coveredness is more restricted than what you have in mind. The notion of coveredness only applies to the quantum channel that you're using. I do not protect the entanglement distribution at all. So I'm assuming there is a network that provides disentanglement for free, on demand, and in a way, the existence of that entanglement is not something I'm trying to hide. So I would argue, though, that the way the problem is defined is legitimate. What you're trying to hide is whether that entanglement is being used to convey information. Like the mere existence of, as you mentioned, common randomness, here entanglement, to me is not a sign that it's being used. So one way to think about the guarantees we offer here, they don't guarantee that there's no entanglement that's being distributed because we take that for granted. But what we guarantee is that if you intercept the quantum signal, you cannot prove that somebody was relying on the entanglement to communicate. Now, the entanglement resource, I think maybe what you're worried about is that effectively it's a secret resource, right? It's not intercepted. Like if the eavesdropper were to tap the entanglement and modify that as well, things become more complicated. There's a way to extend the model to account for that. So for instance, one thing you could do is you could say, let me think about this entanglement distribution explicitly. Bob, on the receiving end, is the one who generates the entanglement. He's going to keep one arm, send the other to Alice through a channel that could be intercepted by the eavesdropper. Then Alice modulates and sends back. So that's a model, it's called a round-trip model, that would capture the fact that the entanglement distribution is part of your system explicitly. And then you can try to hide both the entanglement distribution and the modulation. The results there, I'm happy to discuss offline. We can do a lot of things, but they're much more nuanced and complicated. You define the metric, right, that you care about. I'm not hiding. I mean, here the entanglement distribution is that secret resource that's done offline, and I tap into it. But we could, in principle, look at these models more carefully. But there are a few things out there, so I'm happy to show you what's been done, at least.
Yes, I think for me, it's also fine. So I think in our dreams, perhaps we will have memories and we can distribute entanglement beforehand and then sometimes use it. I want to ask another question. You mentioned this experiment of Xiao. I'm not aware of that. I think he did this experiment perhaps without memory. He just creates the entanglement and immediately also use the transmission part. So okay.
Yeah, so are you trying to get rid of the memories?
No. The question is, are you aware of the experiment where they use also memories?
So the way the experiments are done, and I think that's where all the art of experimentalists kicks in. They generate the TMSV, they do the phase modulation, and then they have a very controlled timing that makes sure that they account for the propagation delay so that in the detector, they use the idler at the correct time to make it interfere in some complicated way with the signal that's coming back. They have a quantum memory because they're delaying the idler in a fiber spool, like putting a photon in a spool and just waiting. That's a memory, but it's not on demand. It's just you have to know the delay, how long you have to keep it. That's and maybe psychiatric and common, but I think that's how most photonic experiments work. I mean, we have to hope, and I think our colleagues are doing great stride. They are really making significant progress in building memories. So we're not yet on demand, but they're going to be able to store photons by doing a transduction to a different domain for longer. The problems then are going to be how efficient is the transduction, or can you read in and read out efficiently? But I think there's real progress there, and you can hope that within the next decade, experiments are going to change. They're going to be not just photonic space, they're going to use different modalities. People already play with these tricks when they want to put signals into mini quantum computers. They already play with that transduction. It's not very efficient yet, but it's coming. So thinking about memories, I think you have to be careful. Like none of what I showed here is doable right now. Probably not realistically even within 10 years, but there's going to be progress. But let me flip things on their head. I think that's an opportunity for us. Because we don't have these ideal systems, we have to do more work to simplify these complicated protocols to make them concrete. So there's a lot of work to do to think about how do you actually do the receivers, how do you actually do the encoding, how do you preserve the entanglement. That's going to be, like a source of many papers for us to write. So I view it in a positive way. We have a lot of work to do. Like if everything, if you could, but it's true in the classical world too, right? If 50 years ago, people already knew how to design a capacity achieving code and build a system that mimics a Gaussian modulation, then there would have been nothing to do. So it took 50 years. So I think my career is safe.
So thanks for the discussion. Thanks also for your talk.